Previously, we used the molar mass equation to do some useful calculation involving chemical formulas. In this video, and the few that follow, we will use the molar mass equation to do some useful calculations involving chemical equations. To do this, we will revisit our understanding of chemical equations and in particular the mole interpretation of a chemical equation. Here we have a balanced chemical equation representing the combustion of the hydrocarbon butane, C4H10, in the presence of oxygen to produce carbon dioxide and water. A mole interpretation of this balanced equation would say that 2 moles of butane will react with 13 moles of oxygen to produce 8 moles of carbon dioxide and 10 moles of water. So a relevant question might be, if we started with 4 moles of butane, how many moles of carbon dioxide would be produced? The ratio of 8 to 2 for the stoichiometric coefficients of carbon dioxide and butane provide the key to helping us with these calculations. So, for example, with a ratio of 8 to 2 or 4 to 1, if we started with 4 moles of C4H10, we should get 16 moles of carbon dioxide produced. If, however, we only started with 1 mole of C4H10, we could use the same approach to show that we would end up with 4 moles of carbon dioxide produced. And if we started with 0.5 moles of butane, we would get 2 moles of carbon dioxide produced. So what we've seen here is that the moles of product can be calculated from the starting moles of reactants by using the ratio of the stoichiometric coefficients in a balanced chemical equation, and that's crucial in our mole interpretation of chemical equations. If now, however, instead of calculating the moles of product produced, we wanted to calculate how many moles of a reactant would be required to react with another reactant, how might we do that? For example, if we started with 2 moles of the reactant C4H10, how many moles of the reactant O2 would be required to completely react with the 2 moles of butane? Once again, we can use the ratio of the stoichiometric coefficients to help, only this time the relevant ratio of the stoichiometric coefficients is 13 to 2, being the coefficients of oxygen and butane respectively. And we've already seen that the answer in this case is 13 moles of oxygen, or O2, would be required to react with the 2 moles of butane. If instead of 2 moles we started with 4 moles of butane, we can use the same ratio to calculate that 26 moles of oxygen would be required. If the starting moles of butane were reduced to 1 mole, we can calculate that 13 on 2, or 6.5 moles of oxygen would be required. And finally, if we started with 0.5 moles of butane, we would see that 3.25 moles of oxygen would be required. In other words, the starting moles of one reactant can be used to calculate the required moles of another reactant by again using the ratio of the relevant stoichiometric coefficients in a balanced chemical equation. So in general, if I'm given the starting moles of substance A in a balanced chemical equation, I can find the moles of substance B simply by using the ratio of the stoichiometric coefficient, and the moles of substance B will actually be equal to B divided by A times the starting moles of substance A, where the lowercase a and lowercase b are the stoichiometric coefficients of substances A and B respectively. Now it's a bit of a mouthful, so this is probably best shown by example. And we'll start by looking at calculating the moles of product produced from a given moles of reactant. For example, if we were given 0.85 moles of butane as the starting amount of moles, we might be asked to find how many moles of carbon dioxide could be produced. The way we would do this calculation is to write a mathematical expression that moles of CO2 produced would be equal to 8 divided by 2 times the starting moles of butane. The 8 comes from the stoichiometric coefficient of carbon dioxide. That's the stoichiometric coefficient of the substance we are trying to find information about, divided by the stoichiometric coefficient of the substance we've been given information about, in this case 2 being the stoichiometric coefficient of butane. And we multiply that ratio by the starting moles of the given substance, which is 8 on 2 times 0.85 moles of butane, and using our calculator, we get the answer that 3.4 moles of carbon dioxide could be produced from 0.85 moles of butane. We can do the same to calculate the amount of reactants required from a given amount of a second reactant. So again, if we were given 0.85 moles as the starting moles for butane, we might be asked to find how many moles of oxygen would be required to react exactly with this amount of butane. This time we would write that the moles of oxygen would be equal to 13 divided by 2 times the starting moles of butane. The 13 comes from the stoichiometric coefficient of the substance we have been asked to find information about, divided by the 2, which is the stoichiometric coefficient of the substance we have been given information about. And we multiply that ratio by the starting moles of butane, which is 13 on 2 times 0.85 moles, and using our calculator we get that answer to be 5.5 moles of oxygen would be required to react exactly with 0.85 moles of butane. In the coming videos, we consider what to do if we were given the mass of a reactant rather than the moles, and we were asked to find the mass of product produced. And we'll see that it is not a straightforward one-step calculation like the one we've just seen.